I love the electromagnetism unit. There's this special kind of comforting order to the development of these ideas, where we look at the fact that a moving charge creates a magnetic field, and then we look at how a moving charge experiences a force in a magnetic field. And now we're going to talk about induction. And induction is really quite an elegant concept. We're going to look at a piece of conducting material, so a metal rod that's sitting in a magnetic field. So here's our magnetic field. I'm really sorry, I always seem to draw magnetic fields that are going into the page. Maybe I just find drawing crosses easier than drawing dots. We're going to put in now this conducting material, this rod, metal rod. So my attempt at drawing a straight line is here. It's not very rod-like, but there we go, did my best. So if we made this rod by some external mechanism move, so we shifted it within the magnetic field. So we're going to draw an arrow here which shows that the rod is moving in the magnetic field. I'm just going to make it a little velocity vector there. So we have a moving wire. What's in that wire? Well, inside the wire there are lots and lots of little electrons. I'm going to draw a few of them down here like this. Those electrons in that wire are free to move. When that wire is moved downwards in the magnetic field, those little charges which are free to move are actually moving at right angles to a magnetic field. And what happens when you get charges moving at right angles to a magnetic field? Yep, they experience a force. So let's use the right-hand slap rule again to work out which direction that force is going. Many fingers, many magnetic field lines. The wires within that bar are moving down the page, so our thumb should be moving down the page. They are negative charges though, so which direction will they be forced? We'll be using the back of our hand. So hopefully you're using your right hand and not your left. You'll find that the back of your hand is pointing towards the left of the page. So you will get a movement of those electrons to the left of the page, and you'll get a build-up of electrons over here. So this end of the rod will become negatively charged, and this end will be left with a dearth of electrons, and that will become positively charged. So I've just summarized that here with some notes. So we've got the moving wire, it actually should say metal rod. So we have a moving metal rod. It has free electrons in the metal rod which move with the rod. There is a force on those electrons. There is a force on those electrons because they're moving in a magnetic field, and as a consequence of that there is a build-up of charge at each end of the rod. What this looks like is a potential difference between the two ends of the rod. Ooh, and what happens if we then connect each end of that rod to a circuit? So let's do that. Here's a wire going out. We'll maybe put a light bulb in there and attach the other end here. And this is why I said before it kind of acts a little bit like a battery. It's a potential difference across the rod, and if we connected to a circuit, those charges would the charges within the wire would be forced from one end to the other, and your light bulb would light up. And this is really, really important. This is important because this is the fundamental idea involved in the generation of electricity, and we're going to get to that in the next week or so. As usual, we're just going to quantify that a little bit. So for a rod of length L, so the rod length L moving across, and I've said across because it needs to be cutting across those magnetic field lines, across a magnetic field with strength B, and it has a speed V. And we can put that together, and you can actually work this out, and for those of you who want to challenge, we can work out what the potential difference is due to those three variables, or those three quantities. So the potential difference between the two ends of that rod, or given the symbol V, it's the potential difference, it's the voltage between those two ends, is equal to the speed that's moving, or the magnitude of that velocity, the magnetic field strength, B, and the length of the rod which is exposed to that magnetic field. And I'll just write down those quantities there with their units. We have the potential difference measured in volts. We have the speed V, measured in meters per second, of course. We have the magnetic field strength measured in Tesla. And we have the length of the wire measured in meters. And you can see that it kind of makes intuitive sense. The faster you're going, the greater that potential difference build-up will be. The larger the magnetic field strength, the larger that potential difference will be. And the length of the wire exposed to the field also will increase the potential difference. You should be able to use this equation in a very straightforward way even before we get to looking at it in more detail in class, and your quiz should test you on those things. Next, we get to Faraday's law, and that's going to require your concentration. So if you've been sleeping up until now, please wake up